Hi everyone, welcome to the Church of Logic. I'm Cody Rue and I'm with Phil Zucker.
Hello.
And today I wanted to talk about the SAT problem and SAT solvers. So, kind of just define the problem at the moment. And then we'll try and talk about kind of deeper things. So, alright, what's SAT? Basically, I mean, at its core level, it's kind of the simple problem of you have a bunch of variables, boolean variables, A, B, C. They can be set to true or false, and then you take arbitrary, logical combinators, right? Or, and, not. Usually you only need those three, but you could imagine a bunch of other ones. Implies, ternary operator, whatever. Imagine whatever you want. And then you have some expression where it's like A or not B and C, right? You have to parenthesize that, but whatever. And the question is, can you set those variables to certain values that will make the whole expression true? I'm saying stuff that's boring, so Phil is nodding and he doesn't have any crucial insights to add at this point. But this is the basic idea.
I have my ways of like pitching these sorts of things. I mean, like the world's used to. There was a time before I got way more into logic and math of the type we do now, and like what logic meant to me was like Boolean algebra is what logic meant to me, and I knew about circuits, I knew about digital circuits even in high school or something, because like I was interested in computers and I was interested in things like that, and I book on it and I like read about it and stuff. I think sort of the idea of like a bit or binary as like a good idea has sort of penetrated society.
Yeah.
And so what the SAT problem kind of lets you do, like people know that there's these digital circuits out there you can run. You can like supply binary values to them and they'll do cool stuff. They'll like add 32-bit numbers together. You can make a circuit that does that out of ands and ors and whatnot, gates that you could build into a chip or whatever. And then like the thing that the SAT problem lets you do, and this isn't directly the definition of SAT, but this is pretty close, that it lets you like run circuits backwards. Like you want to ask, like, is there a way to make this circuit output true? What input would, or output 1, I guess.
Yes.
What input would make this circuit output 1? And then if you had a black box that could do that, it turns out you can solve all sorts of crazy problems. And it's actually a super useful like intermediate format for like solver authors to take in. And then people are interested in other problems to sort of compile a problem down into.
Great. Okay, this is great. This is exactly the point I wanted to like convolutedly make over the course of the next 5 minutes. Running circuits backwards is a great way to express this. I mean, on the face of it, right, just finding a setting of true, false to make your whole formula true, it seems kind of trivial, right? You just like sort of plug in values and, let's try all true. Let's try setting this one to false. And it sounds kind of like a simple problem, but the cool thing is, the rub is that, you look at all these variables, you're like, okay, well, let's try a bunch of values and one of them might work. What if none of them work? That's kind of, that can happen, right? If you have A or not A, and, A and not A, I guess, would be an example. There's no, you can try, true and then false. And that's pretty fast, right? You can imagine doing this with a computer and it's very fast. But then you see as the variables start growing, right? Like, 5 variables is like 32 combinations. And then, and then you hit this thing where, it's exponential, right? There's, for 10 variables, it's, what is it? 1024.
Yeah.
And it grows faster than you can possibly imagine. I was telling this to Phil earlier, but somebody said once, hey, you know what? Chips are really cheap. Let's just throw 500 of them at the problem, and you can solve these really big Boolean formulas. And I was like, no, 500 is tiny, right? You have all these powerful chips and it's great. But as your formula gets bigger with more variables, it just explodes, right? If you have, I don't want to do the math in my head, but if you have like 100 variables, let's see if I have a calculator on this phone.
I mean, the number I like to talk about is 32, because we're used to like 32-bit numbers as sort of being something we want to talk about. And for a 32-bit number, that's about 4 billion possibilities.
Right.
And then you can brute force that on a computer in like a second or under a second, roughly a second. So it's actually kind of cool that you can really brute force, like answer really cool
32
problems
variables
for 32 boolean variables.
Right. But that's 32. It's a tiny number.
But now we're in the 64-bit era, right?
Yeah,
and
that's
like no hope of brute forcing that.
Yes.
Like no way.
So this problem that seems completely trivial, you start looking at it and you're like, wait, I can't even brute force 64 variables, right? And if you're trying to run a circuit backwards, right, those 64 variables are basically the number of wires you have coming into your system. If you look at a computer, right, you're going to get tens of thousands of wires, right? And that is just like inaccessibly huge. And it's exponential, right? It grows faster than you expect, right? This is sort of the defining characteristic of exponential growth, is that it grows faster than you expect, even if you're used to it.
Mm-hmm.
So now we have this problem that's actually really hard. It seemed really easy, now it's really hard. What's kind of cool, and we'll talk about this next time, or in the next episode, whatever, is, hey, it sounds hopeless, but actually, in practice, you can do really surprisingly well at this problem. And that's the miracle of SAT solving.
It's bizarre. It's truly bizarre. It also sort of shows, like, don't ever listen to anybody.
Yes. Try things that seem impossible.
Yeah.
Unless you're about to lose your job and family.
Yeah.
And
okay. Then go the safe way.
Yeah.
But, like, I don't know, people have talked about, and maybe there's an era before SAT solvers became so powerful that, like, once you show something's incomplete, that's time to give up. Like, that's the give up point. And so, it's like, no,
I'll explain what NP complete is in some other episode. But yeah, basically NP complete means it's about as hard as this problem. Something I did want to mention that Phil alluded to in passing is, here's an instance of this problem. You have a Boolean circuit that multiplies two numbers, right? This, of course, is possible because your computer literally has one of those, right? It has a Boolean circuit, a circuit that takes as input, the binary encodings of two 32-bit numbers, and it multiplies them together, right? And maybe there's a remainder or something, or an overflow. But it knows how to take those things and compute the Boolean representation of their multiplication. Hey, guess what happens? If you run that circuit backwards, you input a number, and it's like, hey, give me two numbers that multiply together, give this number. And you could easily exclude the trivial case of just 1 times the number itself.
Mm-hmm.
And so now you have a factoring algorithm. So the factoring algorithm can really be reduced in kind of a very clean, simple way to this, can I find inputs to a Boolean circuit that return 1 or 0, right? Now, of course, the output is more than one Boolean, but you can do this for each bit of the Boolean. So you just need to repeat that 32 times, and that is actually fast. If you have a fast way of computing a single bit of output for that multiplication, then you have a fast way of just undoing the whole multiplication. And so this is a very powerful problem in conclusion. But we know how to solve it in some cases. We know how to solve it very efficiently using really, somewhat clever techniques, but we'll explain kind of the basic techniques, and it's kind of a miracle that this works. And it's also like opens the road to like really powerful applications, not factoring itself, because factoring is kind of a special problem that we've found to be very hard, but other problems that seem to be hard will actually be amenable to these like techniques. Hit me with your insights.
No, that's all right. A great example.
Cool.
It's sometimes it works out. Like, have hope. I don't know, but it doesn't always. Like, if you design problems, or maybe if you get unlucky, the solver won't return.
Yeah. I think there's value in this kind of like conceptual attack, though. This attack the hard problem.